Welcome to e-learning session. So in this session we are going to discuss about the ARM processor instruction set architecture and the ARM register file. So these are the two things which has been going to be discussed in this session. So before actually start with discussing about the instruction set architecture, let us recap what is the ARM processor is. The ARM processor is a simple RISC architecture which adopts load store architecture, and it is a 32-bit architecture, and each the data bus is 32-bit wide, and it supports for 3 different addressing modes. So with that, let's say the actual architecture comprises of a extension of a decoder, instruction decoder here, a register file here, and the ALU we have a max circuit, barrel shifter, and so on. So this is the data bus, and this side we have the address bus connected. So this is what we have discussed in the earlier session. Now in this session we are going to mainly focus on the register file and the various ARM processor states or ARM processor modes we are going to discuss. So these are the two objectives of this session. Now say the data size and the instruction sets of the ARM. So ARM is a 32-bit architecture, and most of the ARM family supports for 2 instruction sets. The 2 instruction sets I call it as a 32-bit ARM instruction set and a 16-bit thumb instruction set. So these are the 2 instruction sets the any ARM family processor supports for. So out of that, the 32-bit I call it as a normal instruction set architecture, or I call it as we normally call it as a ARM instruction set, and the special instruction set we call it as the thumb instruction set. The thumb instruction set actually it's a 16-bit instruction, or in other words each instruction is half a word or 16-bit wide. So that is what we call it as the thumb instruction set. Basically the thumb instruction set is designed say to bring in a high code density and to improve the performance of the instruction set, because all the instructions may not require the 32-bit say encoding. So therefore we have 2 different instruction sets supported by the ARM processors. So the 32-bit instruction set I call it as ARM instruction set, and 16-bit instructions which I call it as the thumb instruction set. So apart from these 2, that is the ARM instruction set and the thumb instruction set, few of the ARM cores or few of the ARM family processors do support for another set of instruction which I call it as the Jazelle processors. These Jazelle cores say can execute the Java bytecodes directly. So this is what we have. So the Jazelle cores say actually the earlier 2 sets, that is the ARM instruction set and the thumb instruction sets, are widely available on all the family or all the ARM processors, but Jazelle is available only on few of the ARM cores, or like the hardware is specially designed in order to support the Jazelle or Jazelle architecture, or I call it as the architecture which supports for the Java bytecode instructions. Our Java bytecodes are 8-bit instructions, and they are designed to be architecture independent. I call it as architecture independent because say the platform independent. So that's why, as we know that Java is a platform independent say language, so few of the ARM cores do support for the execution of the Java bytecodes, and these Java bytecode or the Java bytecode instructions are 8-bit wide. So that means to say these kind of processors which supports for Jazelle, definitely such ARM cores do support for 3 different types of instruction set. The first one is the ARM instruction set, the second one is the thumb instruction set, and the last is the Jazelle code. or Jazelle set. So these are the three different instruction sets which this kind of processors support for. And Jazelle actually it provides transparently it executes the most Java bytecodes in hardware, and some of the instructions are highly optimized and this is due to the trade-off between the hardware complexity and the power consumption will be very less, and the silicon area required will be less, and we could get a good performance from such cores. So this is a specialized feature available on some of the ARM cores. Now coming to the just reiterate the processor states. So we have the processor when it is executing in the ARM state, the normal state. I just say that the normal ARM state support for the execution of the 32-bit wide instructions. That means all the instructions are 32-bit wide. That means to say including the memory access, the instructions which access the memory, like the load instructions as well as the store instructions, they are also of 32-bit wide only. All the instructions, whether it is the instructions to process the data or the instruction which access the memory, all these instructions are 32-bit wide. And such 32-bit wide instruction I call it as the instruction set of the normal ARM state, and all the instructions must be word aligned. When I say like word aligned, what I mean is like each instruction should start from the separate byte address or a byte address which is divisible by 4. So that means to say each instruction will sit in one row, or if I just align the memory as say a 2-dimension comprising of the rows and columns, so column representing the 4 bytes, so nothing but the 32-bit wide, and each instruction will sit in a separate row. That is what the instruction must be word aligned. I think I have the next slide which depicts the diagram of the alignment of the instructions. So we will just again take up that there. So the all instructions must be word aligned, and the PC value is stored in bits 31 to 2, or bit number 2 to bit number 31 are the values stored in the PC, and the bit number 0 and bit number 1 are undefined for this particular state of ARM core, right? And 0, 1 are undefined, bit number 0 and bit number 1 are undefined, and bit number 2 to bit number 31 will be the actual address specified, or the information which is put in the PC, and that gives the indication of the address of the instruction. And say 1 to 0 are undefined as the instruction cannot be half word or say byte long and are byte aligned. So for to indicate that 0, 1 are undefined here, and 2 to 31 are used as the PC value. And coming to the next state of the ARM processor or ARM core, we have the thumb state, and in the thumb state, as just now we said that the thumb state includes instruction set, which are each instruction is of 16-bit wide. So when I say like 16-bit wide, so naturally each instruction is 2 byte long. Each instruction is 2 bytes long, and say all instructions are 16-bit wide, including the instructions which say access for the memory, and all instructions must be half word aligned. When I say like half word aligned, so like for example if say a word comprises of say let me take the initial itself 0, 1, 2, 3 or the 4 byte addresses, naturally the half word aligned, say the instructions should start loading from the byte number 0 or byte number 2, 0, 1 or 2, 3. So any address which is divisible by 2, any word byte address divisible by 2 should be the starting byte from which the thumb instructions gets loaded. So all instructions must be half word aligned, and therefore here the PC value stored is from the bit number 1 to bit number 31, and bit number 0 is undefined as the instruction cannot be byte aligned. So instructions are to be half word aligned rather than byte aligned. So that is what the requirement of a thumb instruction set when it gets into the memory. Yeah. Here I have shown the diagram of the memory organization. So here I have shown a yellow row, yellow field, yellow color field. So the byte number n plus 1, n plus 2 and n plus 3. So these are the 4 bytes occupied by an instruction of ARM state. So this naturally say is permitted, whereas the bytes which are filled with the red color, I have just mentioned it as it is not permitted. So that means these are not word aligned. Saying that an instruction of 32 bit long or 4 bytes will occupy byte number n plus 1, n plus 2, n plus 3 and the next word byte n. So in which case 3 bytes form in one row and the next last byte is occupying the next word. Let me take the example like this is the byte n corresponds to the byte address say 1200, and this becomes 1201, 1202, 1203 and 1204. So these are the 4 bytes. So since it starts from 1201, so naturally 1201 is not divisible by 4. So therefore I say that this is not a permitted combination in order to say place the instruction in the memory. And similarly, the other example I have shown here is it is half word aligned. When I say like half word aligned, the least significant byte of the instruction, that is say B0 to B7 of the instruction is sitting in the byte n plus 2, a byte address which is divisible by 2 but not by 4. Therefore, say 2 bytes, lower bytes are sitting here and the next 2 bytes are sitting in the next row of the memory. So therefore, this is also not permitted say way of loading the instruction. So as I said, in the ARM state or in the normal state of the ARM instructions, the instructions are 32 bit wide, 4 bytes long, and therefore each instruction should get loaded from a new word or should get loaded from a byte address which is divisible by 4. And then coming to the thumb instruction, the thumb instruction should get loaded from a byte address which is divisible by 2. Let me take the example as this as say 1200, 1201, 1202. So 1202 and 1203. So here you find one thumb instruction sitting here and the next thumb instruction is sitting here. So starting from say if this were to be 1200, 1201, 1202, 1203, and naturally the next instruction is sitting from 1204 and 1205 are the 2 bytes occupied by a specific thumb instruction. Whereas this combination is not permitted, wherein the instruction starts sitting from an address which is odd address value of a byte. So starting from that, if an instruction is loaded in the memory, I say that this address from where the first byte of the instruction is sitting is not divisible by 2, or since it is an odd byte address value, so therefore this is not a permitted say way of loading the thumb instruction. So 2 examples I have shown here. So 1 byte sitting here, next byte is sitting here, so which is not permitted. So the Jazelle processor state, as we said, all instructions are 8 bits wide, so definitely I have no restriction. So any instruction of Jazelle state can sit in any byte, subsequent bytes it can sit. So we have are completely whatever the restrictions we had for 32-bit instruction long and thumb instruction, some say restrictions were there as where we can place those instructions in the memory, whereas that is completely relaxed when we come to the processor in Jazelle state. So processor performs a word access to read 4 instructions at once. So that means to say, so every access the processor makes 4 bytes access it makes. So naturally in each access 4 instructions can be brought from the memory into the processor. So we have definitely we get the performance benefit we get. Yeah. So again just to summarize, say the ARM state is first here what I have shown here. So ARM state or normal state of the ARM processor, so for which the processor status register, we have a bit called as T, which indicates whether the processor is working in thumb mode or normal mode or normal ARM state. So for that we have a bit T called as, so if the bit T is equal to 0, it indicates normal ARM state. If the bit T is equal to 1, the ARM processor is working in the thumb mode. Again, let me just make this point very clear. So say it is necessary for the programmer to switch from the ARM state to the thumb state or thumb state back to the ARM state. So this is to be again controlled by the programmer only. Okay, so the instruction set, instruction size when the ARM is working in the normal state, ARM state, when T is equal to 0, the instruction size is 32-bit wide, and thumb instructions when T is equal to 1 in the CPSR, that is the processor status register. So the T is equal to 1 means the instructions are 16-bit wide. And the core instructions what we have in the ARM state is 58 instructions, and in thumb mode 30 instructions. This is taking the example of ARM 7. And the conditional execution. Of course, the ARM processors do support for the instructions which are to be executed conditionally. Let me say the example like move on negative, move n. That means only when it is negative I need to move. So some instructions are to be executed only if a certain condition gets satisfied. So such instructions are available or supported by the processor, and such kind of instructions are the useful instructions or the powerful instructions which naturally decreases or reduces the number of branch instructions. So therefore they are slightly powerful instructions, and such conditional execution instructions in the case of ARM state, most of the instructions do support for the conditional execution, whereas in thumb mode only branch instructions are the one, whereas the other computational instructions we don't get the support of the conditional execution in the case of thumb mode, right? And coming to the data processing instructions, so ARM state do support or do make use of the barrel shifter and the ALU. So access the barrel shifter, each instruction could be passed, or the data operand could be passed through the barrel shifter, and the ALU it just access. So whereas in the thumb mode again we have the instructions can separate, can access the barrel shifter and the ALU. Separate access to barrel shifter and ALU is available even in the thumb mode. And the program status register. So the program status register, so the read and write in privileged mode is available with which the instructions can access to the processor status register in the privileged mode, whereas no such direct instructions are available when the processor operates in the thumb mode. And coming to the register usage, so which we are going to discuss next. So it will access a set of registers and PC. Here also we have set of registers and PC the program counter. So using the program counter, as we know that the program counter always points to the address of the next instruction that is to be executed. So the ARM state will support for or do make use of 15 general purpose registers and 1 PC. So all put together 16 registers, and this side also we have 16 registers, slightly modified version we have. And the Jazelle mode, the instruction size is 8-bit, and the core instructions are almost 60% of the code, Java byte code are implemented in hardware, and the remaining instructions of the instruction set architecture or instruction set say are implemented using the software say implementation or are executed through the software implementation. So this is what the summary of the Jazelle instruction set. Yeah. Now coming to the processor mode. The ARM processor or ARM core will execute the instructions, and it can operate in several say different modes it can operate. Like even in the case of 8086 we have mode 0 and mode 1. So similarly here in the ARM processor we have several mode in which or in a specific mode in which the ARM can operate. So ARM has 7 basic operating modes it has, starting from the user mode which is unprivileged mode or non-privileged mode, and remaining 6 modes are the privileged mode of execution. So when I select normal mode, say any instruction set which an application requires or application execution can be say each instruction of the application can be executed in normal mode, or I call it as the user mode. So user mode is a mode of execution or a mode of the processor in which less privileges are available. So user mode is actually the mode under which most application or few of the operating system tasks are run. So that is what the user mode. Apart from that, we have the system mode, undefined mode, abort mode, interrupt request mode, fast interrupt request, and supervisor mode. So these are the different say modes in which an ARM processor can operate. Each mode has access to its own stack space and a different subset of the registers. So that means to say each mode do make use of few general purpose registers, and apart from that it makes use of some dedicated or some registers which are visible only when the ARM gets into that specific mode of operation. So that is what the meaning here. So each mode has access to its own stack space and a different subset of the registers, and some operations can only be carried out in privileged mode. Some operations same thing as like any other processor. So some of the privileged instructions requires a different mode of execution. So similarly, so in case of ARM also. So coming to the first mode or first privileged mode of execution, we have the supervisor mode. So the supervisor mode of the ARM, so it entered on reset. Every time when the reset instruction comes, the ARM gets into the supervisor mode, and when a supervisor calls instruction, so this specific mode of execution is called for. Or in other words, I will just say that supervisor mode is the mode of ARM processor in which the privileged the kernel instructions gets executed. The kernel instructions definitely do require a privileged mode of execution, and that I call it as the supervisor mode in which these instructions are going to be executed. Now coming to the fast interrupt and interrupt. Say in 8086 also we have interrupts supported and interrupt request, all those things are already we are aware of. So it is same in case of ARM also. But apart from the interrupt request, the ARM say support for the fast interrupt request also. Say it is like this. The fast interrupt, say in some of the processors, say both the fast interrupt and interrupts are available. In some of the other processors also it is available. But perhaps we are not called with a specific name called as fast interrupt. Only in case of ARM, I call interrupt mode and fast interrupt mode. So two different types of modes of operation are available. So in which case the interrupt request mode or interrupt mode is a normal interrupt mode in which the interrupt requests are having less say privileges or relatively they are having the priority level of the interrupts that are available through the interrupt request mode are slightly less compared to the interrupts that are operating in the second mode, that is fast interrupt mode. So fast interrupt mode is entered when a high priority interrupt is raised. High priority interrupt, for that another name given here is fast interrupt. So the highest high priority interrupt instructions naturally will supersede or definitely when the interrupt request is there, and when the next fast interrupt request comes, naturally the fast interrupt having higher priority will mask the interrupt request or the interrupt request which normally operates in the normal interrupt request mode or IRQ mode. So FIQ mode, fast interrupt mode, the interrupts which gets executed in this mode, definitely they have high priority, and these are non-maskable when the processor is operating in the interrupt request mode, IRQ mode, or in the user mode, right, any other mode. So coming to the interrupt request mode, IRQ mode, so this gets, or this mode of execution, the ARM enters when a normal priority interrupt is raised. So due to the device or an instruction state of execution may call for the interrupt or may raise an interrupt and request for the execution of the interrupt handler code or interrupt handler to be executed. The next mode of execution we have is the abort mode. So in the case of abort mode, we have the user, this is used to handle memory access violations. When I say like memory access violation, say the page which is user page or a specific page, beyond that it operates, or the processor gets access into a location or memory which is not, say, specific to that particular task. So in that case the memory violations do call for the execution of the ARM processor into the abort mode. So this is used to handle the memory access violation. So each time when the memory violation occurs, naturally a separate handler has to be executed. And the next privileged mode of execution is the undefined mode. So used to handle the undefined instructions, the instructions which leads to, say, for which the definitions are not available. So naturally the ARM gets into the undefined mode and executes a handler which will indicate that the instruction is undefined. And the next instruction or next processor mode is the system mode, and this is a privileged mode using the same registers as user mode. So the user mode and system mode are slightly, say, a different mode. Only thing is like this is exactly similar to that, but having a privileged mode. That's it. That's the difference between the system mode and the user mode. Some of the operating system routines do require the system mode execution. Yeah. So the summary of the different modes of execution: abort mode, fast interrupt, supervisor, system mode, undefined mode, and user mode. All these different modes of execution, say, do require a specific setting in the CPSR. That means, say, in the processor status register, bit number 0 to bit number 4. So these bits are used in the processor status register. So we need to specify a specific sequence of bits in order to, say, make the processor to enter into this specific mode of execution. The abort mode, the bits which are set from 4 to 0 are nothing but 1 0 1 1 1. So this is the bit setting for the abort mode of execution. And similarly for the interrupt request mode or interrupt mode, IRQ mode, we have the bit number 0 to bit number 4, the 5 bits set are 1 0 0 1 0. So bit number 0 is 0, bit number 1 is 1, and remaining 2 bits are 0, and bit number 4 is 1. So this is what the setting that is expected in the CPSR. So non-privileged mode allows read access to the control field in CPSR, but allows read write access to conditional flag bits or the flag bits, right. So when you select conditional flags, say which indicates the nature of the result of an operation. Yeah. So till now we discussed about the various processor modes. So what are the different instruction sets available? So we said 3 different instruction sets are available on the ARM family processors. So normal mode, thumb mode, and juggle. Then we discussed about what all the different modes in which an ARM processor can operate, user mode and a non-privileged mode, and the privileged modes like fast interrupt, interrupts, and so on. Now coming to the next say architectural feature, say it is necessary to know the register file, because all the ARM processors definitely say forward the operands to the ALU only from the register, right. So no operand could directly enter into the ALU fed from the memory, because this being the ARM being a load store architecture, all the operands are to be stored in the register before they participate in the computation, right. So therefore it is necessary to know about the register file. So the normal user mode supports for the register file comprising of totally 16 registers. So we have 16 registers available, or I call it as the 16 registers are available, which I can call it as the general purpose registers, GPRs. That means to say these registers are visible to the programmer, right. So 16 registers are available for the programmer, or they are visible, right. And along with that we have the processor status register called as the current processor status register, or you call it as current you call, or you call it as present processor status register, nothing but the processor status word what we called in 8086 PSW. So here I call it as CPSR, current processor status register. So each of these register, starting from the first register till the last register of the GPR, general purpose registers, including the CPSR, all are 32-bit wide. So the width of the register is 32 bits. So R0 is 32-bit wide, R1 any register is 32-bit wide, right. So each register we just say number starting from 0 and with a prefix of R. So R0 is the register number 0 and R4 is the register number 4. That means a fifth register I called as R4, because the numbering started from 0. So therefore R0, R1, R2, R4, R7, R9, these are the various general purpose registers which are available, or which are available for the user or the programmer to make use for loading the data and holding the temporary results and forwarding the operands from this file to the ALU, directly to the ALU, or via the barrel shifter we just forward it. So this is what the registers available in the user mode. So one important point we need to note here is like say the ARM processor, since it has different modes of execution, so each mode of execution do make use of a specific say set of subset of this register file, and also each mode do have some special registers which are visible or which are available only when the processor enters into that mode. So that means to say the some of the registers which I have shown here are these registers, all these registers are available only when the ARM processor operates in user mode. And suppose if the processor operates in or say gets switched over to the interrupt mode, So some of the registers may not be visible, or the same register R4, R14 and R13 may not be available. Rather, R13 and R14, instead of this register, we may have a different two registers which are dedicated only for that particular mode of operation. Now, though I said R0 to R15 are general purpose registers in the user mode that are available, but still we have the last three registers, that is R13, R14 and R15. These are the three registers which I call them as the specialized registers. R13, normally it is used as the stack pointer. So user mode do make use of a separate stack, and the top of the stack is pointed by the register number 13. R13 is the stack pointer. That means this always be at the head of the stack. That means it will be pointing to the top of the stack. So that is what R13 register here. Along with that R13 register, we have R14 register, which is called as the link register. As the name says, link. It has to link two different modes, right? Link. So when the processor switches from one mode to the next mode, or say user mode to the interrupt mode, so using this link register, the processor will be able to switch from this mode to the next required mode, and then while coming back from that mode back to the user mode, the link register always helps. That means the link register will be holding the return address. So after execution of the next mode of execution, to come back to the previous mode from where it switched on to the interrupt mode or the privileged mode, and to come back, so it makes use of the link register. And R15 is a program counter, so which will be always pointing to the address of the next instruction that is to be executed. So that is what the PC. So R15 is the PC, a special purpose register or specialized register. Along with that, we have R13 and R14 have specific purpose, stack pointer and link register. Of course, like say, it is not mandatory that this should not be used by the user. So sometimes when the processor is operating in the executing some OS instruction, in such case it may conflict if the R13 is used for the holding any data of the application. So therefore, it is better, say, as far as possible, this should not be used. But however, if it is very specific, very essential, so without affecting the normal execution, so it could be used. But anyway, it requires little special attention of the programmer if at all they want to use these registers. Yeah. So the registers of ARM, actually, as I said, like in the previous we showed that only these registers are available, and I said that there are other registers also available. So in total, ARM has 37 registers. That means to say, in the previous diagram we showed that only R0 to R15 16 registers. Along with that, we had shown CPSR, the processor status register. In total, we shown only, say, 16 plus 1 17 registers we had shown. But now I am just saying here, like the ARM has totally 37 registers, and each register is 32-bit long, and there is a one dedicated register called as the PC program counter, one dedicated register called as the current program status register CPSR, and there are 5 dedicated saved program status register. Sometimes we just abbreviate this as SPSR. CPSR, the current program status register, SPSR, saved program status register, and there are 30 general purpose registers. So when I say like 30 general purpose registers, say in the user mode we had few, and remaining are available only in the remaining 6 different modes of processor operation. So these 37 registers are arranged into several banks. So all the registers are not available as a single bank. So they are spread into different banks. Each bank of the register will come into, say, operational, or will be available only in a specific mode of operation. So in the user mode, we just saw that it contains R0 to R15 and along with that CPSR. That is the complete register bank visible when the ARM operates in the user mode. Now coming to the accessible bank is being governed by the processor mode. That means which bank of register will be active, that is decided by the specific mode in which the processor is going to be operated or will be functioning. So based on that, so the specific bank of the register is governed by the processor mode, and each mode can access a particular set of R0 to R12 register. So we will just see like later. So a particular R13 SP stack pointer, R14 link register, R15 PC, CPSR current program status register, and privileged modes can also access this. A particular SPSR saved program status register is available. So there are 5 different SPSRs available, right? And this is again just summary. The CPSR mode governs which of several banks is accessible. A particular set R0 to R12 and R13 and R14 and so on. A register from R0 to R13 are orthogonal. That means to say, whatever the, say, if I use R0 for holding a data or an operand, so whatever the way I look at R0, so similarly the same functionality, or I can look at any other R1, R2, R3, any register serves the same purpose. So therefore we call R0 to R13 are orthogonal. That means any instruction that we can apply on R0 can be applied on to the remaining registers also. Therefore R0 to R13 are orthogonal, and depending on the context, R13 and R14 can also be used as the general purpose registers. And I said that if at all you want to use R13 and R14 as general purpose, so you should be a little bit careful, right? Now let us say look at the register file again for available for the different modes of operation. Say user mode, we have the registers available R0 to R15, in which case I have already named R13, R14 and R15 as special purpose also. Then we have CPSR, right? And in case of interrupt request, we have a separate register called as R13 and R14. A separate registers are available if the processor enters into the interrupt mode, in which case this R13, which I have along with that I have just named that as a R13 IRQ. I can just name here, I have not shown, but just to make it very specific, I can say that R13 IRQ and R14 IRQ. R13 IRQ is different, physically different from R13 of user mode. This R13 of user mode is different, physically different from R13 of IRQ. So similarly R14 also. So this is a separate exclusive 2 registers which comes into operational only when the interrupt request mode is chosen by the ARM processor. So coming back, say if the interrupt request, fast interrupt mode is called for, then in which case you find that some of the registers of the user mode will be replaced by these registers which are available only in the fast interrupt mode. So let me just show that. So yeah, so this is what we have, right? So R8 to R14, R8 to R14 are going to be replaced. So this R8, R9, R10 and so on up to R14, this which I am showing with a light color, or the fill is not made. So this is what the actual the registers of the fast interrupt mode. So these fast interrupt mode registers, that means a R0 to R7, which are common to the user mode as well as the fast interrupt mode. This becomes the common registers, whereas the higher registers, that is R8 to R14, these are the registers which are dedicated only for FIQ mode, fast interrupt mode. And say I can call this as R8 FIQ, R9 FIQ, R10 FIQ, and so on. So R0, R8 to R15 of the fast interrupt mode registers are replaced or will replace us these registers. That's why the earlier registers which were here, it has been brought out, and these registers are not say visible when the processor is working in the IRQ mode. IRQ mode makes use of R0 to R7 plus R8 IRQ to R14 IRQ plus R15, a common register of user mode only, which is PC and the CPSR, right. And along with that, it makes use of SPSR, a separate register which comes only when the different mode of operations or the privileged mode of execution is called for. So similarly, say I just came back, so fast interrupt mode, some fast interrupt mode when it switches over back to the user mode, these registers will be again visible, and these registers will be not visible, or they just disappear from this bank, right. Say the bank now again whatever that we had in user mode, that was resumed back, and whatever the registers we had in the FIQ mode, so they are now not visible. Now the processor is in user mode, and these are the register, or this is the bank of registers which is visible or which is made use during the execution of the instructions. Now coming to the next mode, say IRQ mode, right, the interrupt request mode, only R0 to R12 are common, and R13 and R14 are replaced by R13 IRQ and R14 IRQ. These two gets replaced, right. These two gets replaced, right. And similarly the SVC mode, right, SVC mode, user mode back, then undefined mode, abort mode, right. Abort mode will make use of R13 abort and R14 abort, two registers will replace the R13 and R14 of the user mode. Say you could see the color, right. So these two registers which were there earlier in the user mode are set aside, and R13 and R14 of the abort mode will be in line with the R0 to R15 or the 16 registers which are visible. So every mode of say processor execution, or each mode of processor state, so 16 registers are available, but some of the registers are dedicated registers of that particular mode. That is what we need to note here, right. So this is the complete register banks available, right. So another demo, say just to make it very clear, so we have shown the user mode to the fast interrupt mode execution. User mode had R0 to R15 plus CPSR, and user mode along with that we had FIQ mode registers available here which are aside, and these are the user mode registers, right. When it switches from the user mode to the fast interrupt mode, an exception is raised, and this exception will make the ARM to switch from the user mode to the FIQ mode. So while transition, so some of the registers gets say replaced, right. So this set of register will get into this subset, right. So that is what we have. So you could see here, say we have R8 FIQ to R14 FIQ here, R8 to R14 FIQ available here, and this register will replace R8 to R14 of the user mode, right. So this is what replaced here. So in the FIQ mode you find that this is actually R8 FIQ, and this being R14 FIQ, right. So this gets say the user mode, some registers are getting replaced by the FIQ registers. So this register will come into this, and this register will be set aside, right. So that is what I have shown in this slide, right. So for to cause the user mode, say switching over of the user mode to any other mode of execution or from one mode to the another mode, the exceptions are raised and the corresponding register subsets will come into action or will be visible, right. So this is what say we have discussed. So in total today in this session we have discussed about the instruction set architecture, in which we have introduced the ARM instruction set, 32-bit wide instructions, the thumb instructions, the 16-bit instruction set, and then Jazelle instructions. The instructions are of say 8-bit wide, which supports for the execution of the Java bytecode, and we have also discussed about the different modes of operation. So privileged modes of operations, there are several, and we have user mode. So user mode, along with that interrupt mode, fast interrupt, system mode, and so on, and what all the bits that are to be set in the process status register in order to activate each specific mode of operation of the processor. We have looked into that, and later we have discussed about the different register file and the different banks of the registers that are available in the ARM processor. So there we looked at so totally there are 37 registers and different banks of registers, and in each bank we find specific registers available, and general purpose registers of user mode are also visible in the respective modes of operation. And CPSR and SPSR, these are the again two say process status registers, and CPSR is maintains the process status, and every time when the exception is raised, the CPSR is pushed onto the SPSR, that is the saved program status register, and again when it switches back or comes back, the SPSR is to be resumed into the CPSR. So this goes or this is how an ARM instruction set and the register file looks like, right. So thank you.